If you work in urban planning or landscape architecture, you really feel this core tension that our sources are highlighting today.
Oh, absolutely.
It's this rapid shift away from relying on, heavy gray infrastructure, your concrete pipes, your dikes, to something more flexible.
More adaptive.
Exactly.
Yeah.
I mean, historically, we just built our way out of water problems. But now, with climate change driving these extreme weather events, we're realizing you can't fight water with concrete.
You have to fight water by managing the water itself.
And that is the crucial shift.
It is. And it brings us right to this concept of the sponge city. At its most basic level, a sponge city uses nature-based solutions, NBS as planners call them, and green infrastructure to manage stormwater.
Forget the complex engineering models for a second.
Right. The definition is actually beautiful and simple. It's a city that's designed to adapt flexibly, just like a natural sponge, to environmental changes. It soaks up water, it filters it, and then it slowly releases it back into the natural system.
Or makes it available for reuse.
Precisely.
And since so many of you listening are coming from the school planning world, our mission today is to give you that strategic blueprint for building these kinds of resilient urban environments. We've synthesized a really comprehensive landscape planning study from a project in Germany.
An Asian Development Bank briefing on the global policy side?
So we're going from the technical decisions, right up to the big institutional hurdles. Okay, let's get started and really focus on the technical heart of it, this idea of the stormwater treatment train.
Right, but before we jump into the solution, we have to be crystal clear about the problem. And that is the disruption of the natural hydrological cycle.
Evaporation, infiltration, runoff.
Exactly. In a natural area, a forest, a meadow, water mostly evaporates or it infiltrates down into the soil. You get very little runoff. But urbanization, it just seals those land surfaces.
Roads, sidewalks, parking lots.
Roofs. All with these impermeable layers. And that immediately prevents infiltration, which means we're cutting off our vital groundwater systems from their source.
Yeah. And the data on that impact it's just shocking.
It really is.
Our sources indicate that the rate of rainwater runoff in these super sealed urban areas can be twice.
Or even 3 times that of a natural vegetated area. It's a huge difference.
You put a number on it for you?
Yeah.
If a site has, say, 75 to 100% impervious surfaces, over half of the water, 55%, becomes rapid surface runoff.
Compare that to natural ground cover, where it's less than 10%. That gap, that delta, that is your urban flood crisis in a nutshell.
And that rapid, high-volume runoff creates 2 really distinct and devastating threats.
It does. First, there's the obvious one, the physical flood risk. But second, and this is just as important, is the water quality threat.
Because the stormwater is washing over all those surfaces.
It acts like a solvent. It picks up major contaminants. We're talking heavy metals from cars, oil residues, fine sediment, and then excess nutrients like nitrogen and phosphorus.
And when that contaminated flow hits our rivers and lakes,
it threatens the entire aquatic ecosystem. It's what fuels things like harmful algal blooms. And the real headache for planners is that this is overwhelmingly non-point source pollution.
Right, you can't just point to a single pipe and say, that's the problem.
No, it's coming from everywhere. And that makes it incredibly hard to control with the old gray infrastructure methods.
So that kind of systemic problem, it demands a systemic solution. And that brings us to the core philosophy here. Low impact development, or LID.
LID is the operational strategy that really gives the Sponge City concept its muscle.
And the key is that strategic integrated approach you mentioned before, the stormwater treatment train.
Right. It's a sequential system. You're integrating various rainwater management facilities so you can treat the water over distance and over time. It's not a single fix.
It's a process.
Exactly, a process. We can break it down into 4 main techniques that manage the water's journey. First up are protection techniques.
That's about source control, right? Stopping runoff before it even starts.
Precisely. Then you have retention techniques. These focus on storage, just holding the water until it can either infiltrate into the ground or evaporate back into the atmosphere.
Okay, so that's long-term storage.
It is. And then you have detention techniques. This is more like temporary storage holding water just long enough to slow down that peak flow before it drains somewhere else.
And finally,
conveyance techniques. These are simply about moving the water safely and efficiently from where it falls to where it's going to be collected and treated.
So how do these 4 strategies actually look in the real world, in the urban landscape?
Well, that's where you get into the specific facilities, the train cars, as you called them, things like green roofs and permeable pavement.
Let's start at the top then. With green roofs, they seem like the ultimate protection technique. They immediately cut down on runoff quantity and rate.
And they're fantastic at mitigating the urban heat island effect, a huge co-benefit.
And for you planners, you're typically looking at two types, and it usually comes down to structural capacity.
Right. You have your intensive green roofs. These need a deep substrate layer, often 200 millimeters or even more. That lets you plant a high diversity of things, even shrubs and small trees.
But the maintenance is higher, and the structural load on the building is a serious engineering question.
A very serious one. The alternative is the extensive green roof. It uses a shallow substrate, and you're typically using really robust, resilient species like sedum.
Lighter, less maintenance, and they're great for conserving stored water.
Yeah, the choice there is almost always dictated by the building's existing structural tolerance. You have to work with what you've got.
Okay, so moving down from the roof to the ground level, we've got permeable pavement. This feels critical for all those parking lots, walkways, low traffic areas.
It is. It lets the runoff percolate right through the pores or voids down into the soil layers below, which enables that infiltration and eventually bioremediation.
And we're dealing with four main types here: pervious concrete, porous asphalt.
Permeable interlocking pavers, and then those concrete or plastic grids.
So what's fascinating here is not just the material itself, but how you choose it. For a planner, what are the key selection criteria? It's not just cost.
Right. Not at all. It revolves around flow rate, durability, and maybe most importantly, maintenance. Porous asphalt, for example, can handle really high flow rates, but it needs rigorous vacuum sweeping to stop it from clogging.
And clogging is the real Achilles heel here, isn't it?
It absolutely is. Clogging is the #1 failure mechanism.
So if you don't design pre-treatment systems like a filter strip or a swale to get the core sediment out before the water even hits the pavement,
your system's lifetime is just drastically reduced. It forces you to think of this as an integrated system, not just, a material you're laying down.
Okay, so connecting all these facilities, you have these sequential purification procedures. The treatment train is designed to handle pollutants in stages.
That's right. The primary stage is all about physical screening and letting things settle out. You're just targeting the big stuff, gross pollutants, coarse particles.
Filtering out the leaves and trash.
Basically, yes. Then the secondary stage gets into the fine sediment, the heavy metals, and nutrient removal. And that's where the soil and the plants really start to do the work.
And finally, the tertiary stage deals with whatever is left, the dissolved substances, to make sure the water is as clean as possible before it's discharged or reused.
And this is where it gets really interesting, because the element that's so often overlooked when we talk about green infrastructure is what's happening below the surface.
Right.
The real workers in this entire system aren't the engineered pavers or the roof membranes. It's the soil and its massive population of microorganisms. Without healthy soil, the whole train just stalls.
And a major indicator of a healthy functioning soil is its soil organic matter, or SOM.
Yes.
And that's all the organic material in the soil decomposed leaves, microbial biomass, everything except the living above ground plants.
And the benefits are huge. SOM improves soil structure, it reduces compaction, it dramatically increases water infiltration and storage.
And crucially for planners, it helps eliminate or chemically bind the very pollutants we're trying to remove.
That binding capacity is tied directly to a couple of key biological processes. First, you have phytoremediation.
Using living plants to actively clean up contaminants.
Right. Plants absorb and store mineral nutrients and even heavy metals in their tissues. It's a process called phytoextraction. So if you're dealing with heavy metals, you can literally remove the pollutant from the site by just
harvesting the plants.
Harvesting and removing the contaminated plant matter. Then you also have bioremediation. This uses the living microorganisms, the fungi, the bacteria that are abundant in healthy soil, to break down complex contaminants.
Into harmless stuff like CO2 and water.
Exactly. But there's a key restriction here.
And this is a critical note for the planning audience.
It is. Bioremediation is generally not suited for projects dealing with really high concentrations of things that are toxic to the microbes themselves.
Like the heavy salts used for de-icing roads in the winter.
Or high concentrations of cadmium or lead. That specific constraint dictates some really crucial design decisions, which we'll see very clearly in the German case study.
But before we get there, we have to talk about the biggest urban impediment to all of this.
Soil compaction.
Yeah. Pressure from construction equipment, constant traffic. It increases the soil's bulk density.
Which crushes the pore spaces. It drastically reduces water infiltration, limits nutrient uptake, and stunts root growth. If water can't get into the soil, the sponge just fails.
But there's an elegant solution for this, especially in high-load areas like under sidewalks where you want to plant trees. It's called structural soil.
Right. It's the specialized base course where you mix crushed stone aggregate with soil. The stone forms a rigid matrix that can support the traffic load, which prevents the compaction.
But the soil fills the gaps in that matrix, maintaining void spaces for roots to grow and water to be stored.
It's a perfect integration of gray and green infrastructure at the microdesign level, load-bearing and ecological function all in one. For large street trees, our sources recommend an optimal depth for this structural soil layer of about 60 to 90 centimeters.
Okay, let's pivot from these technical details to a real-world application. This really helps illustrate what risk-informed planning looks like. We're looking at this landscape planning project in Leinefelde-Worbis, Germany.
It was designed for the 2024 State Garden Exhibition, and this new garden city site, about 6.3 hectares, it faced some immediate environmental
The
challenges.
subsoil conditions were not great.
Not at all. The ground is mostly low permeability. We're talking an infiltration rate of no higher than 1 times 10 to the negative 6 meters per second. Very slow.
And the critical water problem was that untreated runoff from the urban area was just being discharged through old sewer pipes directly into the Yonne River.
Which then feeds the Birkinger Reservoir, a crucial drinking water source. So threatening that reservoir was the central environmental issue they had to solve.
So the core strategy they adopted was an aggressive application of these LID principles with one primary goal: find an effective, integrated solution to prevent that water pollution.
And their core strategy was almost militant about it. The complete separation of rainwater from the sewers, no runoff was allowed to enter the existing combined sewer system, period.
So they built their treatment train.
They did, very carefully. They mandated green roofs and permeable pavements for source control. And then for conveyance and treatment along the streets, they chose enhanced vegetated swales.
So open, grassy channels that filter water as it moves.
Exactly. The design was meticulous. The main 3 streets, which are about 16.5 meters wide, integrated a really substantial 2.7-meter wide vegetated swale.
And the final purification stage, where does that happen?
That happens in the South Green Park. It uses a massive bioretention area, over 2,190 square meters, designed as a deep-layered biofilter, a combination of a filter strip and a rain garden.
And since the goal wasn't to create a permanent pond, but to purify and discharge the water quickly, the rain garden was the right tool.
It was the perfect detention mechanism before the water was routed safely into the Yonne River.
But the most important technical insight here for planners, it comes from the design of one specific part of this system.
The East Rain Garden, yes. This area was designed specifically to collect runoff from high-traffic sources, especially the Bundesstraße 247 bypass.
Where you're going to get high concentrations of those de-icing salts we mentioned, chloride and sodium.
The very things that are toxic to microbes and can contaminate the groundwater. So, to mitigate that very specific risk, the East Rain Garden was designed as a biofilter system with an impermeable liner.
So it's sealed at the bottom.
Completely sealed. This prevents any of that highly contaminated water from infiltrating into the native soil. It routes the flow through the biofilter layers and then safely out without poisoning the crucial groundwater below.
That one decision just perfectly illustrates how a specific risk assessment has to override the generalized goal of green infrastructure when an acute pollutant is present. So Leinefelde-Worbis shows the technical precision you need. But the global picture from the ADB brief really highlights the massive institutional scale of this challenge.
Especially concerning the People's Republic of China's ambitious Sponge City program. I mean, the PRC's national target is an incredibly aggressive 80% reduction of urban runoff in their cities.
But that enormous ambition is hitting some significant institutional headwinds. And these are challenges that planners everywhere have to deal with.
They are. The experts identified several systemic problems. First is fragmented investment.
So lots of small, isolated projects.
Exactly. Little islands of green infrastructure that lack systematic citywide coverage. So when a major flood still happens, like that devastating event in Zhengzhou in 2021, it creates this public and political perception that the entire Sponge City concept failed.
When really the scale and the coordination just weren't there yet.
They were completely insufficient for an event of that magnitude. Second, you have acute departmentalization. This is policy paralysis.
Different departments working against each other.
Yes. For example, the Land and Resources Department might want to preserve existing farmland, which directly contradicts the space the Urban Development Department needs for, say, riverfront green infrastructure to manage flood risk.
Contradictory objectives that just stop integrated solutions in their tracks.
And the third one is just pure systemic inertia. There is a deeply embedded, decades-long bias toward traditional gray infrastructure.
Concrete drainage systems.
It persists in municipal engineering handbooks, in construction standards, even in the professional qualifications of engineers. Overcoming that entrenched mindset is just incredibly difficult.
And that systemic inertia, it directly impacts the planner in the field. I mean, if your local engineering handbook doesn't even recognize structural soil or bioretention systems as acceptable,
Then you, as a planner, even armed with all this knowledge, are legally constrained. You default back to the old, traditional, less resilient systems.
precisely.
And that really highlights the opportunity here for advancing the concept globally. The focus has to be on reforming that entire policy, regulation, engineering, construction nexus.
It's not just about building things differently.
No, it's about prioritizing evidence-based learning, using advanced hydraulic modeling and simulation tools like they did in the Jilenyanji project to quantify flood risk, and truly integrating this resilience planning across entire city clusters and river basins. It's a systems problem that needs a policy systems solution.
So the Sponge City really is the ultimate low-impact development strategy. It successfully turns stormwater from this devastating threat into a valuable resource, but only through these systematically integrated green and gray systems.
It demands a completely holistic approach.
Right, from the choice of permeable paving in a single parking lot, all the way up to the city-scale institutional coordination needed to make it work.
And I think the key lesson from these planning materials is that successful urban water management requires that meticulous technical planning. We saw how they calculated the precise bioretention volume in Leinefelde Orbis.
That wasn't just a random number.
Not at all. It was the calculated safety margin. And you have to combine that with a deep understanding of natural processes like soil health and bioremediation, and then aggressive policy reform to break down those departmental silos.
So if knowledge is most valuable when it's understood and applied, we want to leave you with this final thought. If the biggest hurdle really is this policy inertia, what single non-infrastructure spending policy change could your local planning department implement tomorrow to break that dependence on gray solutions?
It's a great question.
Maybe mandating that all new construction site plans have to include a detailed analysis of the existing soil organic matter content, or a requirement to use native plant species in all stormwater facilities to support local ecology. You should explore ways to institutionalize the Sponge City philosophy without just relying on a big capital budget.
That is the definition of holistic planning.